Introduction. As we look around the room, we see most objects by the light reflected from them in order to converge to bring the parallel rays of light closer or diverge to spread out the parallel rays of light. This phenomenon of converging and diverging is done by spherical mirrors. The mirrors having curve-like surfaces are known as curved mirrors. Objectives. At the end of this lesson, you'll be able to define spherical mirrors, understand the types of spherical mirrors, understand the reflection of light by spherical mirrors, concave mirrors and convex mirrors, differentiate between concave and convex mirrors, how to form images, know the sign convention for mirrors, define magnification. Introduction of curved surface. A spherical mirror is that mirror whose reflecting surface is the part of a hollow sphere of glass. Spherical mirrors are of two types: concave mirror and convex mirror. Concave mirror. A spherical mirror in which reflection takes place at the bent in surface is called concave mirror. Convex mirror. A spherical mirror in which reflection takes place at bulging out surface is called convex mirror. Important terms to understand spherical mirrors. Center of curvature. It is the center of the hollow sphere of glass of which the mirror is the part. Pole. The center of a spherical mirror is called the pole. Principal axis. The straight line passing through the center of curvature and pole is called principal axis. Aperture of the mirror. The portion of mirror where reflection of light takes place is called aperture of the mirror. Principal focus. The point on the principal axis to which all the light rays are parallel and converge after reflection is called the principal focus. Focal length. It is the distance between the pole and the principal focus. Rules for obtaining images formed by concave mirrors. Relationship between the radius of curvature and focal length is F is equal to R upon 2. Rule 1. A ray of light which is parallel to the principal axis passes through its focus and after reflection from the mirror. Rule 2. A ray of light passing through the center of curvature reflects back along the same path. Rule 3. A ray of light passing through the focus then becomes parallel to the principal axis after reflection. Rule 4. A ray of light incident at the pole is reflected back making the same angle with the principal axis. Formation of different types of images by concave mirror. When object is placed between pole P and focus F, image is formed behind the mirror, virtual and erect, larger than the object, magnified. When object is placed at the focus F, image is formed at infinity, real and inverted, highly enlarged. When the object is placed between focus F and the center curvature C, image is formed beyond center of curvature, real and inverted, larger than the object. When object is placed at the center of curvature C, image is formed at the center of curvature C, real and inverted, same size. When object is at infinity, image is formed at focus, real and inverted, smaller than the object. Uses of concave mirror. Concave mirror are used as reflectors in torches, vehicles, headlights, and searchlights. Shaving mirrors to see large images of the face. Dentists to see large images of the teeth of patients. Rules for obtaining images formed by convex mirror. Rule 1. A ray parallel to the principal axis of a convex mirror appears to be coming from the mirror. Rule 2. A ray going towards the center of curvature of a convex mirror is reflected back along the same path. Rule 3. A ray going towards the focus of a convex mirror becomes parallel to the principal axis after reflection. Rule 4. A ray incident at the pole is reflected back making the same angle with the principal axis. Every time the image has following characteristics. The image is formed behind the mirror. It is virtual and erect. Smaller than the object. Formation of different types of images by convex mirror. When object is at infinity, image is formed behind the mirror. It is virtual and erect, smaller than the object. When object is placed anywhere between pole P and infinity, image is formed behind the mirror. It is virtual and erect, smaller than the object. Uses of convex mirror. Convex mirrors are used as rear view mirrors in vehicles to see the traffic at the rear side because it always produces erect image. The size of image is small and so we can see a wide field of view of traffic behind. Mirror formula and calculations. Mirror formula is the relationship between the image distance v, object distance u, and focal length f. 1 upon v plus 1 upon u is equal to 1 upon f, where u is the distance of object from mirror, v is the distance of image from mirror, f is the focal length of the mirror. Sign convention for spherical mirrors. All the distances are measured from pole. Distances are measured in the same direction of the incident light is taken positive. Distances against the direction of incident light is taken negative. Distances measured upward and perpendicular are taken positive. Distances measured downward and perpendicular are taken negative.
Refraction of light. The speed of light changes when light rays travel from one medium to another medium. In this process, light rays bend when they pass at an angle from one medium to another. This phenomenon is called refraction of light. Refraction of light can occur by two ways: rarer to denser medium. When light rays travel from a rarer to a denser medium, then velocity of light decreases in the denser medium. Hence, light rays bend towards the normal. Denser to rarer medium. When light rays travel from a denser to a rarer medium, then velocity of light increases in the rarer medium. Hence, light rays bend away from the normal. The refractive index. The speed of light in different substances varies. Therefore, different substances have different abilities to bend or refract light. This bending ability of a material is known as the refractive index of that material. Refractive index of a medium is the ratio of velocity of light in vacuum to its velocity in a given medium. The refractive index of a rarer medium is less as compared to that of a denser medium. Laws of refraction. There are two laws of refraction. First law: the incident ray, the refracted ray, and the normal to the surface separating the two media at the point of incidence all lie on the same plane. Second law. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media. This law is also known as Snell's law. Sin I upon sin R is equal to mu, where mu is a constant called refractive index. Snell's law is not applicable when the ray is incident along the normal. Refraction through a rectangular glass slab. Consider a rectangular transparent slab made of a material of refractive index n. Let a ray of light PQ enter from air at Q. This ray is refracted at the upper surface of the glass slab and moves along QR within the slab. At R, it gets refracted again and emerges into the air. By Snell's law, at point Q, n is equal to sin I upon sin R. At point R, n is equal to sin E upon sin R. From equation 1 and 2, we get sin I upon sin R is equal to sin E upon sin R. This gives I is equal to E. Therefore, when a ray of light passes through a transparent slab with parallel faces, the emergent ray is parallel to the incident ray, but it is displaced. This displacement is proportional to the thickness of the slab. Refraction by spherical lenses. Lenses produce images similar to those formed by curved mirrors, but they do so by refracting light. Lenses are either convex or concave in form. Convex lenses are thickest at the middle. Concave lenses are thickest around the edges. Most lenses are made of glass and have spherical surfaces. Light rays passing through a convex lens bend towards the principal axis, whereas rays passing through a concave lens bend away from the principal axis. The rays passing through the convex lens converge to a point F. The rays passing through the concave lens diverge as if traveling outwards from a point F. F is the principal focus of the lens, and the distance from F to P is called the focal length. Rules to draw ray diagrams for spherical lenses. Rule number 1. A ray of light through the optical center of the lens, O, passes undeviated through the lens. Rule 2. A ray of light parallel to the principal axis passes through F when it leaves the lens. Rule 3. A ray of light through F' leaves the lens parallel to the principal axis. Formation of images by convex lens. When the object is placed at infinity and the rays are parallel to the principal axis, then the image formed at principal focus on the other side. The nature of the image is real, inverted, and diminished. When the object is placed at infinity and the rays are not parallel to the principal axis, then the image formed at the focal plane on the opposite side of the lens as that of object. The nature of the image is real, inverted, and highly diminished. When the object is placed beyond 2F, then the image formed on the opposite side between F and 2F. The nature of the image is real, inverted, and diminished. When the object is placed at 2f, then the image formed at 2f on the opposite side. The nature of the image is real, inverted and same size. When the object is placed between 2f and f, then the image formed beyond 2f on the opposite side. The nature of the image is real, inverted and enlarged. When the object is placed at f, then the image formed at infinity. The nature of the image is real, inverted and enlarged. When the object is placed between f and the optical center, then the image formed on the same side. The nature of the image is virtual, erect and enlarged. Formation of images by concave lens. When the object is placed at infinity, then the image formed at f on the same side. The nature of the image is virtual, erect and diminished to a point. When the object is placed at any distance, then the image formed on the same side between optical center and f. The nature of the image is virtual, erect and diminished. Sign convention for spherical lenses. The sign convention rules are as follows. Rule number 1. All distances are measured from optical center. Rule number 2. Distance measured in the direction of incident light is positive and distance measured against incident light is negative. Rule 3. Distances measured above the principal axis are positive and distances measured below the principal axis are negative. Rule 4. According to sign convention, focal length of a convex lens is positive and that of the concave lens is negative.
Magnification produced by lenses. The ratio of the height of image to the height of object is known as linear magnification. Magnification is equal to height of image h2 upon height of object h1. M is equal to h2 upon h1, which is equation 1. If magnification has plus sign, image formed is virtual and erect. If magnification has minus sign, the image formed is real and inverted. The linear magnification is equal to the ratio of the image distance to the object distance. M is equal to V, image distance, upon U, object distance, which is equation 2. Equating equation 1 and 2, h2 upon h1 is equal to V upon U. Note, in mirrors, linear magnification is M is equal to minus V upon U, and of lenses is M is equal to V upon U. Power of lenses. The power of a lens is measured by the degree of convergence or divergence of light rays falling on them. Convex lens converges the beam of light falling on it and focusing them to the optical center. It has the greater power. Concave lens diverges the beam of light falling on it and making it less strong. Power of lens. The power of a lens is defined as the reciprocal of its focal length in meters. Power of lens is equal to 1 upon focal length. Important points. The power of convex lens is positive. The power of concave lens is negative. Power of combination of lenses. If a number of lenses are placed in close contact, then the power of the combination of lenses is equal to the algebraic sum of the powers of individual lenses. P is equal to P1 plus P2. The SI unit of power of a lens is diopter. It is denoted by the letter D. Did you know Light exerts physical pressure on objects in its path. Light pressure is equal to the power of light beam divided by c, the speed of light. It is written in the Rig Veda that light consists of 3 primary colors. Mixing the 3 colors, they have produced all the objects of sight. Summary. Let us summarize what we have learned. In concave mirror, the reflection takes place in the bent-in surface. In convex mirror, the reflection takes place from the bulging out surface. The radius of curvature of a spherical mirror is the radius of the hollow sphere of glass of which the mirror is the part. The focus of a convex mirror is situated behind the mirror. The image is formed at that point where at least 2 reflected rays intersect. A real image is always inverted and virtual image is always erect. Large concave mirrors are used in the field of solar energy to focus sun's rays for heating solar furnaces. The object distance u is always negative in mirrors. A medium in which the speed of light is more is known as optically rarer medium.